Precalculus, review of algebra prior to calculus part 4, domain, equations and inequalities. This series I've developed looking at the inspiration from Canadian math teacher Jeremy Clausen. I invite you to look at his video lessons. I'm taking mostly the very same examples that Jeremy has in his lessons, but I'm imparting, as usual, my own emphasis to these lessons. So check that out. So part 1 here to this video lesson is going to be finding the domain of certain functions. And here we have y is equal to the square root of quantity 3x plus 4. And so can we take the square root of a negative number? Well, yeah, we can, but then we would have an imaginary number for that answer. And so what we're looking for in calculus is mainly real numbers. So we're going to take within this square root bracket this quantity 3x plus 4, and for what values is 3x plus 4 defined? Well, we have to have this quantity here, 3x plus 4, not negative. So not negative translates to greater than or equal to 0. And so if we go ahead and solve this inequality, and we have 3x is greater than or equal to negative 4, and we have x is greater than or equal to negative 4/3. And so in interval notation, how do we write this quantity? We write this as negative 4/3, bracket negative 4/3, comma, infinity. And that's one way we could look at it. Another way is if we take this function and consider the function inside the square root bracket as y equals 3x plus 4. If we graph this particular function, if we have an xy coordinate plane, we would have an x-intercept here at x equals negative 4/3. And if we graphed this function here, we would get this looking type of line here. I'm drawing in red. And we could see the value of this function would be positive at greater than x equals negative 4/3. So graphically, translating this to a graphical representation of what's inside the square root bracket can be helpful as far as figuring what is really going on here. Next, we have y equals 1/4 x cubed plus 3x squared minus 5. Now what kind of function is this? Well, this is a cubic function, but the cubic function within the greater family of what we call polynomial functions. What is going to be the domain of this polynomial function and all other polynomial functions? Well, it's going to be all real numbers. So we would write the domain of this function as an interval notation as negative infinity, comma, infinity, and that would be it. Okay, polynomial function. Okay, all real numbers. So that should be helpful to us. Next, we have this one, y equals the square root of quantity x squared minus 9. So we have to have this quantity inside the square root bracket and set this equal to greater than or equal to 0. And so we can work this out a number of ways. One thing we can do is we can factor the left side of this inequality as using difference of squares as quantity x minus 3 times quantity x plus 3 is greater than or equal to 0. But we have a combination of things here to consider. We can, as I did earlier, consider this graphically. If we consider the x squared minus y as a function, y equals x squared minus 9, we would graph that function by looking at the x-intercepts of this function and drawing the parabola representing this. So we want to find where this value is greater than or equal to 0. Well, where do we see that? Do we see that we have the y-axis? So where are we looking? Are we looking to above the x-axis or below the x-axis? Okay, so what we got to have is above the x-axis is where we're going to have greater than or equal to and also including. So what we would do is we could write down x is greater than or equal to 3, and also x is less than or equal to negative 3. And another way we could do this problem is just by algebraically considering this x squared minus 9 is equal to 0, or let's say greater than or equal to 0. If we add 9 to both sides of this inequality, we have x squared is greater than or equal to 9, and taking the square root of both sides, we're going to have x is greater than or equal to plus or minus 3. And so what we're going to have is this is going to branch off in two directions. We're going to have x is greater than or equal to 3, but also we're going to have x is less than or equal to negative 3. So how did we come up with this x is less than or equal to negative 3? Well, it's simply that when you divide or multiply by a negative number, which in this case we did when we took the square root of 9, we change the direction of the inequality symbol. So anyway, that's how we consider this particular problem. Let's go on to D. Find the domain of the function. Basically, we have this y equals 5 over 2 minus x, and so we are looking for this rational function with our variable in the denominator. So we look for exclusions to our domain. And how do we find our exclusions? Well, what do we know that we cannot divide by in math or in algebra? We cannot divide by 0. So therefore we know that 2 minus x can equal everything but cannot equal 0. And if we add x to both sides of this equation, we're going to have 2 or x cannot equal 2. So that is our exclusion to the domain. And so what this really looks like here is if we have a number line and mark on that number line 2, we know that x cannot equal 2, but it can be anything greater than 2 or anything less than 2. So in interval notation, we would articulate this domain as greater than negative infinity up to 2, and then also 2 to infinity. And what do we place in between these intervals? We place a u for union. So that's what this would look like. Okay, here we have e. We have 1 over a square root of quantity x plus 3, and for a square root bracket, do we put in x plus 3 is going to be greater than or equal to 0? Does that seem right? Well, no, it's not quite right, because not only does x plus 3 have to be greater than or equal to 0, it actually has to be greater than 0. Now why do we have to have this also greater than 0? Well, that's because we cannot have 0 when we have this expression in the denominator. So therefore x has to be greater than negative 3. And so we would articulate this, the domain of this function, thusly. We would say, oops, I put a bracket, is that right? No. Greater than is going to be a parentheses. So we put negative 3, comma, infinity, and this would be our domain for part E. Next, F. We have y equals the negative of the absolute value of quantity x minus 5 over 2. When we consider this absolute value function, or any absolute value function, do we have any limitations to the domain included, such as like an irrational function or a square root function? No, we don't. So even though this function has what could initially look to us like quite a degree of complexity, we should be able to see that it's permissible to put in any real number value for x and still make this a valid portion of the interval of the function. So in this instance, our domain is going to be all real numbers. Okay? Now we get to part 2, which is going to be solving these equations. And we have this quadratic trinomial, 3x squared plus 9x minus 30 equals 0. When we look at factoring, we should look at, first of all, if there is a greatest common factor that applies to each of these terms. And if we think about it, there is. So we can factor out a 3 from each of these terms and be left with 3 times quantity x squared plus 3x minus 10 equals 0. And I hope you'll be able to see that if we divide by 3, each side by 3, we would be able to essentially get rid of this 3 by doing so. And so what we're left with is x squared plus 3x minus 10 is equal to 0. And how do we do this? Well, the easiest way to solve problems I've found out is by factoring, if we can. So, and if we can't factor, we can look at other things. But we're looking for what here? We're looking for two numbers which when multiplied together equal negative 10, but when added together equal 3. So we're going to have to get a negative 10, we're going to have a plus and a minus. And I'm thinking 5 and 2, and 3 is a positive, so I'm thinking quantity x plus 5, quantity x minus 2. So these will be our this will be our factored form, and then we can use the zero factor property to rewrite this as x plus 5 equals 0 and x minus 2 is equal to 0. And so therefore x is equal to negative 5, and also x is equal to 2. So that's what we have here. Now there's another way yet to work this out graphically, like we talked about. If we consider this a function here that we factored out the 3 from as y equals x squared plus 3x minus 10, and we graphed this function side here, and we have our x-intercepts of y equals negative 5 and y equals 2, what does the graph of this look like? Well, the graph of this parabola will look like this. I think we intersect here at negative 10, our y-intercept, and comes up. And so this parabola represented by the function y equals x squared plus 3x minus 10 intersects the x-axis at x equals negative 5 and x equals 2, and hence our solution set. And you can also write this in set notation as x equals negative 5 comma 2. So you'll see solutions written this way also. Okay, B, we have 4x cubed plus 3x squared equals 16x plus 12. And what we want to do to solve equations usually is to set one side of an equation equal to 0. So if we subtract 16x and 12 from the right side of the equation, we do the same on the left side of the equation. And so we're left with 4x cubed plus 3x squared minus 16x minus 12 is equal to 0. Now this is a cubic function that is not going to be, we look for a common factor, we don't see it. So this is a situation that we have to use another technique, and a possible technique would be something we haven't done much of in Precalculus last year. That's called factoring by grouping. And so if we look at just taking this portion here, these first two terms, and these last terms, what do we know? What do we see? Well, we could see that we have that 4 is to 3 has the same aspect ratio to 3 as negative 16 has to negative 12. And so therefore we could rewrite these two terms on the left as the common factor between these two is going to be x squared times quantity 4x plus 3. And then for these terms on the right, what we're looking for is to see if we can take the factors that would also give us 4x plus 3. So if we write here 4x plus 3, what number times 4x will give us negative 16x. Well, it's going to be minus 4. And it so happens that negative 4 times 3 is negative 12. So this will be our factoring. We have a common factor now, so we can rewrite this expression on the left as quantity 4x plus 3 times quantity x squared minus 4. And x squared minus 4 we can further factor as quantity x plus 2 times quantity x minus 2 is equal to 0. And so therefore, if we work this out, we're going to have 4x plus 3 is equal to 0. And so if we subtract 3 and divide by 4, x is equal to negative 3/4. And also we have for x plus 2 is equal to 0, x is equal to negative 2. And lastly, if we have x minus 2 is equal to 0, we're going to have x is equal to 2. So these would be our solutions. Now another way we could work out this type of problem is using the rational roots theorem and trying possible rational zeros out. And then when we get a remainder of 0, we know we have a root. So let's go to this problem C first. Okay, we have 2x squared minus 10 equals 0. So what is be our common factor between these two terms? Well, 2. So 2 times quantity x squared minus 5 is equal to 0. And as we did in problem 2a, we can just rewrite this to solve for x as x squared minus 5. Now, this binomial on the left is not classically factorable as others we've seen, but we can sort of force the issue here by still using our difference of squares to rewrite this expression as x plus square root of 5 times quantity x minus square root of 5. And so therefore x can be equal to negative square root of 5, and x can be equal to square root of 5. So that's a possibility, and we'll have a chance in calculus. We'll run across this once in a while. Okay, now for D, we have a cubic polynomial function, and as opposed to B, where we were able to factor by grouping, this one we don't see a pattern of a ratio like we did in B. So we have a coefficient of 1, coefficient of 4, and then a coefficient of 1, and a coefficient of negative 6. So that's not going to work out. So what I suggest using here is something called the rational roots theorem. And if you recall last year, or wherever you took precalculus, I hope you went over the rational roots theorem, and that is the possible rational zeros are going to be plus or minus the factors of the last term over the factors of the coefficient of the first term, plus or minus. So we're going to have, what are your possible factors of 6? Well, are going to be plus or minus 1, comma, plus or minus 2, comma plus or minus 3, comma plus or minus 6. Now in a cubic function, we're only going to have at most 3 possible rational zeros, or zeros period, and so we can try these out. So if we try x equals 1 as a possible rational zeros, that would correspond to the factor of x minus 1. Okay, so if we plug in, if we treat this as a function and we put in f of 1, what are we going to get when we plug this back into x cubed plus 4x squared plus x minus 6? Well, we're going to get 1 cubed plus 4 times 1 squared plus 1 minus 6. And what is this going to be equal to? Well, 1 plus 4 plus 1, that's 6, minus 6 is 0. So therefore, this factor of x minus 1 is a factor. And this might look a little bit intimidating, but I hope you can see that it really shouldn't take very long, if there are answers here, is to go through these pretty quickly to get a rational root and hence a factor. So we know that. Let's go ahead and figure out what the rest of this would be, and we can take our real zero of 1 out here and put the coefficients of all the terms inside this synthetic division bracket of 1, 4, 1, and negative 6. So we bring down this 1. So we're going to get 1x squared. 1 times 1 is 1. 5. 1 times 5 is 5. We get 6. And then 1 times 6 is 6. And we get our remainder of 0. So what we know is that we have quantity x minus 1 times quantity x squared plus 5x plus 6. And that's going to be equal to 0. And then, I'll bring this up here, we can factor this x squared plus 5x plus 6 as quantity x plus 2 times quantity x plus 3. And that is going to all be equal to 0. So we're going to have x is equal to 1, x is equal to negative 2, and x is equal to 3. So we can write this in set notation as x equals it's negative 3. X is equal to negative 3. Negative 3, negative 2, 1. Is it 100% necessary to write in set notation these numbers in order? No, but conventionally it looks prettier this way, to go from the numbers from lowest to greatest, least to greatest. Okay, next we have E. We have x to the 4th power minus 5x squared plus 4. And again, we're looking at a cubic, this is what we call quartic function, to the 4th power quartic. Now, what happens, this one could be challenging to factor, but if we lower the power of this expression, we can rewrite this expression on the left in quadratic form. And we can do that by saying let x squared equal another variable a. And if we do that, x to the fourth power we can rewrite as a squared. And then we could have minus, and if we let a equal x squared, 5a squared and plus 4 are equal to 0. And can we factor this expression now? Yes, we can. We can do that as a. So what two numbers add to 4, or add to negative 5, but multiply their equal 4? Well, are going to be negative, negative. So we have 1 and 4. So we have a is equal to 1 and a is equal to 4. And now we can take our x squared equals a back, and we can rewrite this as x squared is equal to 1, and also x squared is equal to 4. And then taking the square root of both sides here, we can write this as x equals plus or minus 1, and also x equals plus or minus 4. So this is how we're able to use substitution to find solutions. So occasionally we'll have the opportunity to do that. And so now we have f, a rational equation. So how do we solve rational equations? We do it by clearing out the denominator. But what we have to also look for is possibilities of what x cannot be exclusions. So if we look at our denominators, remembering that we cannot divide by 0, we should see that x cannot equal whatever makes the denominator 0. So x cannot equal negative 4, nor can x equal 5. So these restrictions are going to remain with us no matter how manipulations may make us forget them. And so what is our common denominator going to be? Well, we can get our common denominator by multiplying these two denominators together. So our common denominator is going to be quantity x plus 4 times quantity x minus 5. And so let's rewrite these values. So if we take x minus 3 over x plus 4, what can we multiply by to get our common denominator? Well, our denominator, if we multiply it by quantity x minus 5, we have our common denominator, but we have to do what also? We have to multiply our numerator also by quantity x minus 5. And we had to also wrap our values in parentheses. And then we take minus, we have x plus 2 over x minus 5. And to get our common denominator, what do we have to do? Well, we're going to have to multiply our denominator by x plus 4. And having done that, we have to likewise multiply our denominator by quantity x plus 4. And so now, this is what we have. And we can go ahead and multiply these together, these binomials together. So we're going to have x squared, then we have minus 3x minus 5x, we're going to have minus 8x, and then negative 3 times negative 5 is going to be plus 15, and then we're going to have minus what all these are here. I'm going to go ahead and put all this in parentheses. We're going to have x squared, and then 2x plus 4x will be plus 6x, and then we're going to have plus 8. And then all this over our common denominator of quantity x plus 4 times quantity x minus 5. And then just continue to work below here. We're going to have x squared minus x squared will cancel each other. And we're going to have negative 8x minus 6x. So we're going to have negative 14x. And then we're going to have 15 minus 8, which is going to be 15 minus 8 is going to be 7. So we have negative 14x plus 7 over quantity x plus 4, x minus 5. And that's still going to be equal to 0. See, we've maintained our 0 throughout. Now we multiplied through, we didn't find our common denominator, really have to do, we are equal to 0 where the value of our numerator is 0. So we come here and having reduced our numerator to negative 14x plus 7, the numerator is equal to 0. So we can take, if we add 14x to both sides, we're going to have 14x is equal to 7. So we're going to have x is equal to 1/2. And we look at our exclusions. Sometimes the solution we find will be equal to our exclusion, but in this case it is not. So therefore our answer to this equation is going to be x equals 1/2. Okay, next G, we have 5 over x minus 1 equals 12 over x squared plus 1 minus 1. And so what are going to be our excluded values? Okay. Well, we know that x minus 1 cannot equal 0, so therefore x cannot equal 1. And we also know that in this denominator on the right side, we're going to have x squared minus 1 cannot equal 0, so therefore x plus 1 times quantity x minus 1 cannot equal 0. And we already found the exclusion that x cannot equal 1, but also we're going to find x cannot equal negative 1. So these would be our excluded values. And what is our common denominator going to be here? Our common denominator is going to be this x squared minus 1, which I'm going to rewrite as quantity x plus 1 times quantity x minus 1. So let's go ahead and rewrite our fraction accordingly. We're going to have first 5 times, or 5 over x minus 1. And how do we get this to our common denominator? We're going to have to multiply our denominator by quantity x plus 1. And likewise do that in the numerator. So there's one of them. Then we have minus 1. And so what do we have to do to get our common denominator? We have to multiply the denominator by x minus 1 times quantity x plus 1. And here we have this in the numerator, likewise x minus 1, x plus 1. And now we're going to the right side of the equation. We have 12, and we already have x squared minus 1. Or let me rewrite this as which is going to be, I want to rewrite this in the form, the factored form. We're going to have x, 20x minus 1, x plus 1. Okay, and then we do this the same way here in the, well, we already have that denominator, so we're already good to go on this. So we can just rewrite all of this. So we're going to have 5x plus 5 minus, we're going to have x squared, so we have minus x plus x, and so we're going to have x squared minus 1, and that's going to be equal to 12, and all these are going to be over this common denominator of 20x minus 1, x plus 1. So really we just have to worry about what's in the numerator here. So we're going to have 5x minus x squared, and then we're going to have 5 minus 1, which would be plus 4, is equal to 12. And then what I recommend doing is, we have this negative x squared, so I recommend taking everything over to the right side of the equation, and we'll do that by adding x squared, subtracting 4, and subtracting 5x. And when we do that, I'm going to work over here, arrow over here, we're going to have, and on the other side we do the same thing, which would be minus 5x plus x squared minus 4. We're going to have 0 on the left now equals x squared, and we're going to have minus 5x, and then we're going to have 12 minus 4 equals 8. Okay, so do we have a factorable? What are the factors of this right here? X, is this factorable? What are the two factors that add up to, we're going to have a minus, right? How about 2 and 4, 1 and 8? So we might have to go ahead and use the quadratic formula for that. Not sure. Yeah, that looks right. We have minus minus. There's something amiss here. Minus, well, that's minus, but this would be plus. Okay, I know a number's off somewhere. So we're going to have 5x plus 1, so that's going to be 5x plus 6. And if we minus 6 instead, let's see if this works differently here. So we're going to have we're going to have 12 minus 6, so we'll have 6 here instead. Yeah, it didn't work out, so I knew there was some kind of mistake here. So we're going to have 2 and 3. And so therefore x is equal to 2 and x is equal to 3. Are those part of the excluded values? No, they are not. So we can write this in set notation as x equals 2, 3 in brackets. Okay? So now we're going to solve inequalities. And this really becomes important in calculus. We'll do this quite a bit, but reinforcing the skill. Now you remember earlier in this video lesson, what we did is we figured out that what if we set this equation here, this left side of this inequality equal to the function y equals 3x plus 10, and we graphed that function. Well, if we did that, we would have, if we wrote this as 0 equals 3x plus 10 to find the x-intercept, we would have x is equal to negative 10 thirds. And so we could we could draw this situation as our y-intercept and mark it at negative 10 thirds, and then we have a positive slope here, so here would be a line that comes right through this x-intercept of negative 10 thirds, and we want to know where this function of 3x plus 10 is greater than. Well, the function is going to be greater for any number greater than negative 10 thirds. So x is greater than negative 10 thirds. Okay? So that's one way of looking at it, just to change in a graph. Or just strictly algebraically, you can put 3x is greater than negative 10 dividing by 3, x is greater than negative 10 thirds. So same way in either case. Okay, here we have 2x plus 1 is less than or equal to 5x minus 11. So we can subtract from each side of the inequality 2x and 1. So we're going to have 0 is less than or equal to 5x minus 2x, or 3x, and negative 11 minus 1 is going to be minus 12. And so 3x, and adding 12 to both sides, we have 12 is less than or equal to 3x, and dividing by 3, we're going to have 4 is less than or equal to x. So therefore x is going to be greater than or equal to 4. And we can rewrite this in interval notation as bracket 4 comma infinity. So there we would have our answer for that. And we could work this out graphically too. Graph the function 3x minus 12, figure out where that would be. Okay, we have now C. We have quantity x minus 1 and quantity x plus 4 is less than 0. So what I want to do here is find out, we're going to find the zeros here. So we have x minus 1. We're going to find out where this value on the left is equal to 0. So if we change this to an equation, we're going to have x is equal to 1, x is equal to negative 4. So if we draw a line here, we can put our zeros on this x-axis at -4 and at 1. And then if we represent this as a xy coordinate plane, this is what it would look like. xy. And what do we have here? Well, we're going to have an x squared. So we're looking at a polynomial function, an even-natured polynomial function that is positive. So that's going to be this, something looking like this right here. Okay, we want to find out where this value on the left is less than 0. Well, I hope you can see that the value of this as a function is going to be less than 0 between -4 and x equals -4 and x equals 1. So we would write this as our x is equal to our interval from greater than -4 to 1, but not including 1. And I'm going to show you also another alternatively a way of doing this. If we write this out as a number line and put -4, comma 1 over here, we can put the sign above the x-axis and figure out where it is. So we can try different numbers. So if we try a number less than -4, we're going to have, say, -5. Well, we would have a negative times a negative, or be positive up here. Between 4 and 1, we can plug in 0. And if we plug in 0, we would have negative times a positive, which would make a negative. And to the right of 1, we would have a positive times a positive. So that means that only in this interval, in the middle between -4 and 1, do we have, is this a true statement? So we could diagnose our answer this way as well, using a sign chart. And that's the way we're going to be doing that quite a bit in calculus later on. Okay, next we have x squared minus 7x plus 6 is greater than or equal to 0. And so we can go ahead, we hope, factor this expression as xx. So what two numbers do we add together to equal -7 but multiply together equals 6? Well, 1 and 6. So again, we have the situation, if we look at this as a graph of a quadratic function, we're going to have x is equal to 1, x is equal to 6. So we can put this, put an xy coordinate plane here at 1 and x equals 6. And then we can take and draw our parabola, and we are interested where the value of the function is greater than or equal to 0. So we would find that at x equals 1 and to the left. So x is going to be less than or equal to 1, or x is greater than or equal to 6. So that's one way of looking at that. And again, we could pull out our sign chart and do the same thing that we did earlier between 1 and 6, and then we could take a value less than 1, say 0, we would have a positive times a positive. And then between 1 and 6, if we took 2 for instance, we'd have a positive times a negative, and then to the right of 6 we would have a positive times a positive. So in this instance we would find the same conclusion. Okay, next. Okay, we have quantity x minus 4 squared times quantity x minus 2 times quantity x plus 2 is less than or equal to 0. So what type of function total do we have here? What do we have? Well, I hope you can see that we would have x to the x squared times x times x. So our leading term here would be x to the 4th power. And x to the 4th power is what type of polynomial function? Well, it's going to be an even positive function. And what that means for us, an even positive function, is that we're going to start high and end high. Let's go find our zeros. X is equal to 4, right? Solving this for 4. X is equal to 1, and x is equal to negative 2. And we can go mark our values. So negative 2, 1, and 4. And understanding that we're going to have to start high, end high, with our leading term being x to the 4th power, what we look for is the multiplicities of each of these zeros. Well, for this 0 of 4, we have a squared. So this is going to be multiplicity equals 2. And then for x equals 1, we're going to have multiplicity equals 1, and for x equals negative 2, we're also going to have multiplicity equals 1. So what does that mean? Well, the values of the multiplicities will tell us if the graph of the function touches or crosses the x-axis. So we're going to have to come from on high, and we're going to come and touch. The first zero we're going to look at is this negative 2. So we're starting from on high, we're coming down and touching at negative 2. Now at negative 2, with a multiplicity of 1, are we touching or crossing the x-axis? Well, that's an odd number multiplicity, so we're going to cross the x-axis. And then we're going to come down and approach our next zero, which is 1. Now, the 0 of 1, what multiplicity does that 0 have? Well, it has an odd number multiplicity, so we're going to cross the x-axis. Now we're going to come up here and come down and touch the 0 of 4. Now at 4, do we have an even number multiplicity or odd number multiplicity? Well, two things. We know we have an even number multiplicity, and also we know we're going to have to finish high, because the leading coefficient of the 4th power means we have to start high, end high. So we're going to come up here like this. And so where do we have the inequality satisfied? Well, between negative 2 and 1, and also at 4, because we're touching. So we're going to have, our answer here is going to be x equals, we're going to have our interval from negative 2 to 1, and including, because we have this less than or equal to, and also this value of 4. So you have a union here of 4. And in classic interval notation, that's how we would represent that 4. And we can also do a sign chart like we did on the prior problems, which would be C and D. We could do the same type of analysis. So next, let's look at this one here. We have x squared is less than 3x. So we can rewrite this expression and subtract 3x from both sides and rewrite this as x squared minus 3x is less than 0. And we can factor out an x times quantity x minus 3 is less than 0. And so we'd have x is equal to 0 and x is equal to 3. And we can put this on a number line and put 0. We can actually make this like, do this as xy. So 0 and 3. And what we would have here is a parabola with an x-intercept at 0 and also an x-intercept at 3. And we want to know where the value is less than 0, which would be below this x-axis. So our solution is going to be x is equal to the interval between 0 and 3. And so that would be how we do that particular problem. Okay, next, G, we have x squared is greater than or equal to 7. So we can write this as, again, we could subtract 7 from both sides. We could rewrite this expression or inequality as x squared minus 7 is greater than or equal to 0. And so we can now use the difference of squares on the left side and write this as quantity x minus square root of 7 times quantity x plus square root of 7. Let me make a little more space here for that. I'm using the bigger pen here. X minus quantity square root of 7 times quantity x plus square root of 7 is greater than or equal to 0. So we would have, again, if we looked at this graphically, we would have on the left side negative square root of 7. On the right side we would have positive square root of 7. And we would have between them, okay, upward opening parabola. I didn't quite cut it. And so we're going to have positive or equal to, so for this situation x is going to be less than or equal to negative square root of 7, and also x is greater than or equal to positive square root of 7. So that's how we would quantify that. Or in interval notation, how would we write that? Interval notation, we'd write this negative infinity, comma, negative square root of 7, union, square root of 7, comma, infinity. So that's another way we can articulate our answer to this inequality. Next, we have this expression here. We have quantity x plus 1 times quantity 2x plus 1 times quantity x minus 6 is greater than 0. So we're going to have as our zeros here x is equal to negative 1, and then for this 2x plus 1 we're going to have x is equal to negative 1/2, and then we're going to have x is equal to 6. So what this looks like, we can use our same analysis tools. We could already go ahead and put in plus or minus, but the number line is what's helpful to us. So we put a number line here, and in order we're going to put negative 1, negative 1/2, and 6, and see what happens here. Now what we're going to have, if we multiply all these x values together, we're going to have our leading term of this expansion is going to be 2x cubed, and that's going to be positive 2x cubed. So we're going to start low and end high, and since each of these zeros occurs only once, we know that each has a multiplicity of 1, meaning that we're going to cross the x-axis in every instance. So starting low, we're going to come up here, touch and cross the x-axis at negative 1, come down, touch and cross the x-axis at negative 1/2, come way down here, and then at 6 we're going to touch and cross the x-axis one last time. And so where do we have the inequality greater than 0? Well, we're going to have x is equal to the interval between negative 1 and negative 1/2, and also greater than 6. So 6 comma infinity. So this would be the intervals where this inequality is true. And now I, which is the last one that we'll be doing this exercise set today, we have quantity x plus 1 squared times quantity x minus 2 times quantity x plus 4. I invite the viewer to go ahead and see if you can work this out, then follow up and see if you got it right. Okay, the first thing we're going to have, first zero we're going to have is x is equal to negative 1, and that 0 is going to have a multiplicity of equal to 2. And then we're going to have x is equal to 2, that's a multiplicity of equal to 1. And then we're going to have x is equal to negative 4, multiplicity is equal to 1. So that should give us something to go on. And then to figure out what our leading term is going to look like on the left side, we're going to have x squared times x times x. We're going to have x to the 4th power. So what is that going to mean? Well, it means we're going to start low and end high. So let's go ahead and write this out. We have, mark our zeros here. We're going to have negative 4. We're going to have negative 1. We're going to have also, no, there's a multiplicity, yeah, okay, we got a multiplicity of 2. I was getting a little worried. Then we have 2. So we're going to start high, end high with x to the 4th power. So we come down here from high, and we go and we touch at negative 4. Now, with this multiplicity, with this 0, are we going to touch or cross the x-axis? Well, we have a multiplicity of 2, meaning we just touch and do not cross. So the graph of our function is going to bounce off the x-axis, come up here, and go to negative 1. Now, negative 1, is that going to be, okay, negative 4. See, I got this wrong. Let me go ahead and back up. That's why we do this. Okay, negative 4, we have a multiplicity of 1. Okay, So we're actually going to cross the x-axis. I was able to catch myself because we had a multiplicity of 1. Now we come up to negative 1. Are we going to touch or cross the x-axis? Now we have our multiplicity of 2, so we're going to bounce and go down, and we're going to come down here, and at 2, are we going to touch or cross the x-axis? Multiplicity of 1, we cross the x-axis. So now we can see above or equal to the x-axis is where this inequality is true. So we're going to have x is equal to, we have the interval, and again equal to is included, so we can write this as between negative 4 now, oh, we're looking for greater than, excuse me, oops. I lost something there. Let me go ahead and erase this. Yeah, so x is equal to, we want above here, so we're going to have above or equal to. So we're going to have negative infinity to negative 4, but including negative 4. So we're going to bracket that negative 4. And also we're going to have negative 1. Oops, we need to bracket that negative 4. There we go. And also we're going to have that negative 1. So I'm going to bracket negative 1. And then union greater than 2. So we're going to have greater than or equal to 2. So we have 2 comma infinity. So there we have it. What we're doing here today, especially in this 3, solving inequalities, is going to be extremely helpful to us as we go into differential calculus later this year. I hope this has been helpful to you. Good luck, and thanks for viewing.